let's take a look at trig equations and all the different identities and formulae that we now know can use. Compound angle formulas. The sine, cos, sine. If it's the sine, it's the sine. So cosine, cos, sine. If it's not the sine, it's not the sine. And then tan plus tan on 1 minus tan. From there we all got double angle formulas. Sine 2 theta, 2 sine theta, cos 2 theta, and there were 3 different ways we could do that one. So we could also write it as 2 cos squared minus 1, which led us to the cos squared theta result, and 1 minus 2 sine squared, which leads us to the sine squared theta result that we looked at yesterday with integration. And tan 2 theta, 2 tan theta on 1 minus tan squared theta. Then the half angle results, or the t results. So if we let t equal tan of half of the angle, then we can say tan theta is 2t on 1 minus t squared, sine theta 2t on 1 plus t squared, cos theta 1 minus t squared on 1 plus t squared. Then we looked at products to sums, 2 sine cos, 2 cos, and 2 sine. How do you remember these ones? Remember, of course, you do have the resource sheet. If you do forget, you can always look them up. But sine cos must have come from sine, because that's our expansion for those ones. And so it's sine plus sine. Cos must have come from cos, so that's cos plus cos. Sine's the one where we've got to be careful with. It's sine. It must have come from cosine. But because we know cos had the plus, that means that the sine must have the minus in the middle. But the other thing to look at is, look, they swap around on this one. So you could think of it that way if you prefer to keep the sum as the first one, and so it becomes minus cos A plus B plus cos A minus B. Just got to be careful with that one. And going back the other way, sine plus sine, 2 sine half sum cos half diff. Cos plus cos, 2 cos half sum cos half diff. And cos minus cos. Now that's the one that's a bit different because it's got the minus in there. So therefore this now is a bit different. Starts with the negative rather than the positive. And whereas sine plus sine starts with sine and cos plus cos start with cos, because this one's a bit different. Cos minus cos starts with sine. But also because it's different, the other two end off with cos, this one ends off with sine. Okay, it's just how my mind works. But there's our sums to products. And a reminder, those ones are not actually on the reference sheet. They are if you think about it, because you could always read the products to sums backwards, I suppose. So they sort of are there, but hidden, if you like. Okay, so the idea behind solving trig equations, right? We want to get all the angles the same first of all, because just like any equation, we're trying to make whatever it is, we're trying to find the subject of the formula. Then match the required answer range, okay, to whatever the angle is. They might tell you that theta goes between 0 and 360, but if the angle's 2 theta, then you've got to look between 0 and 720. Get all the trig functions the same, again, so you can make it the subject of the formula. And if you're ever in doubt what to do, just change everything to sines and coses. That usually allows you to play with it. Always check your answers, because a lot of times with trig equations, I mean this is true for any equation, but a lot of time with trig equations you transform it into something else to make the solving easier. And so is the solution an answer to your transformed equation, or is it an answer to the original equation? So always just check your answers. Okay. Starting off with the very basic ones. So cos 2 theta is a half. We're going between 0 and 360. So therefore, because it's 2 theta, I'm going to go between 0 and 720. It's in quadrants 1 and 4. I'm going to find this acute angle, which is 60 degrees in this case. And therefore, the one I'm trying to find, it's in the first quadrant, so it will be that acute angle. Or it's in the fourth quadrant, so it'll be 360 minus that one. There's our possibilities. Remember, we're going around the circle twice, so I end up with 4 possibilities. But that's for 2 theta. Divide everything by 2. We get our answer. But of course now we've got other ways we could do that question, because we have results for cos 2 theta. I could have changed it to 2 cos squared theta minus 1's a half and make cos squared the subject, which means cos theta will be plus or minus root 3 on 2, which now means I'm in all 4 quadrants because it's plus or minus, so I still end up with 4 answers. The acute angle becomes 30 degrees now because we're saying the cos is root 3 on 2, so putting that into all our quadrants, we come up with those same 4 answers. Okay? Then ones like this. Oh, I've got 2 different types of trig, so I'll use the trig identity. We know about sec squared. Sec squared is 1 plus tan squared. We turn it into a quadratic, and that one factorizes nicely. Tan x is either minus a quarter or it's equal to 1 as well. So let's look at the minus a quarter. It's negative. Okay, I know I'm in the second or the fourth quadrant, which means the acute angle would be 14 degrees 2. In the second quadrant, 180 minus that. Fourth quadrant, 360 minus that. Okay, I've got my first 2 possibilities. Now, tan x equals 1. Well, that's positive, so this time I'm in the first or the third quadrant. There we go. The acute angle is 45 degrees, and I get another 2. Remember, don't leave those answers hanging there. Pull it all together into a final solution. I like to put them in numeric order. I suppose you don't have to, but it just seems a more logical thing to do. So there's my 4 possibilities for x. Okay, another cos 2 theta 1, but on the right hand side I've got cos squared and I've got sine squared as well. So it probably makes sense to use the cos squared minus sine squared for the cos 2 theta in this one, because now I can turn this into tan squared, because of course sine on cos being tan. Tan theta plus or minus root 3, so I'm in all 4 quadrants. We go and find our acute angle, in this case 60 degrees, put it into all 4 quadrants. We got our 4 answers. Alright, let's look at some that have appeared over the years. So back in 2000, cos 2 theta, yet again cos 2 theta, is equal to sine theta. So this time it makes sense to change the cos 2 theta to 1 minus 2 sine squared. I've got a quadratic, factorise it, 2 possibilities. So the first one, sine theta is a half, first or second quadrant, acute angle is 30 degrees. Let's put it into the quadrants. Sine theta equals -1 is a boundary angle. So I know that's 270 degrees if I think of my graph. So I only have 3 answers for this one. 2 sine squared this time is sine 2 theta. So we'll change the sine 2 theta. We'll use our double angle there. That becomes 2 sine theta cos theta. It is a quadratic, factorizes, so either sine theta is 0 or sine theta is cos theta. Alright, well, the first one's a boundary, but remember, when you're talking about the ends of the boundary, if 0 is a solution, well 360 is going to be a solution as well, because you've gone around the circle, you're back in that same spot. So be careful for that answer of 0. If 0 is an answer, 360 is an answer as well. Now for the other one, sine equals cos. Let's turn that into tan. So it's just tan theta equals 1, which is our exact value of 45 degrees. Put it into the quadrants, and this one has 5 answers. Sine theta sine 3 theta is equal to half. So I've got a product. I want to turn it into a sum. So this one becomes, well, it's sine, so it must have come from cosine, and so one's going to be the sum, one's going to be the difference. Well, the sum of the 2 is 4 theta. Oh, hang on a sec, sine. That's the one that's a bit different. So it's negative it starts off with rather than positive. Okay, so the sum, 3 plus 1 obviously is 4. The difference, 3 minus, is 2. In this one, it actually doesn't matter the order, because cosine's an even function. So had I gone theta minus 3 theta, I would have got cos minus 2 theta, but being an even function, that is the same as 2 theta. So with cosine, it doesn't matter which way around we do the subtraction. Okay, let's now go and attempt to solve that. I'll use a double angle on the cos 4 theta. I've now got all the angles the same. We've ended up with a quadratic, but remember, theta's between 0 and 2 pi. I'm finding answers for 2 theta. So I'm going between 0 and 4 pi. Factorises quite nicely. So cos 2 theta equals 0. That's, again, a boundary value. I'm going to have pi on 2, 3 pi on 2, but I'm going around twice. So I add 2 pi to each of those. 5 pi on 2, 7 pi on 2. Divide everything by 2. Okay, equals a half. That's one of our exact values of pi on 3. Put it into our first and fourth quadrant. Again, going around the circle twice. So we end up with another 4 answers. Now, because they're in radians, fun putting these in order. Hang on, which one's bigger than which? There's our order. We go pi on 6, pi on 4, 3 pi on 4, and so on for all our possibilities of that one. It was was a nice little one from a couple of years ago. The numbers a, b and c related by a is b minus d and c is b plus d. And d is a constant number. We have to show that the sine of a plus the sine of c over the cos of a plus the cos of c is the tan of b. Well, let's substitute in what they told me a and c were. Now you'll notice at the top we have the sum of two sines. On the bottom we have the sum of two coses. So I can turn that into a product. I'll go sum to product. So sum to product. The top one, sine plus sine, so we've got 2 sine, half sum, cos half diff. On the bottom, cos plus cos, 2, cos half sum, cos half diff. Well, cos of negative d or cos of d doesn't really matter. Again, it's an even function, but they're going to cancel. I'm left with sine on cos, which is indeed the tan of b. Okay, that was the first part of the question. The second part was even better. Hence or otherwise, solve this equation. Oh my goodness. Well, remember, hence or otherwise means you can do it any way you like. But hey, let's use part A. It's probably going to be the easiest way of doing it. That's probably why they got us to do it in the first place. So there's the equation. Okay. Remember, we showed that this expression we can transform to be the tan of b. So I want to work out what b is. b minus d was a, and a in this case is 5 theta on 7. And b plus d was c, and in this case that's 6 pi on 7. But basically, if I just leave them as a and c for now, I can get the b as a plus c on 2. And that works out to be 11 theta on 14. All right. I'm looking for answers between 0 and 2 pi, which therefore means I'm looking for 11 theta on 14 going between 0 and 11 pi on 7. At least they've given us an exact value, so root 3, which means I'm in the first or the third quadrant. The exact value is pi on 3 and 4 pi on 3, but how many times round of the circle am I going? 11 pi on 7 is not around the circle yet, is it? So I don't need any more solutions. And 4 pi on 3 is less than 11 pi on 7, so I do include both of these solutions. Divide both of them by 11 on 14, and we get these wonderful answers, 14 pi on 33 and 56 pi on 33. Yes, the numbers don't always work out to be nice. Okay, so 11A, just a bit of a recap on trig equations.